You know, when you sit down at your laptop, type a quick prompt to have an AI like draft a strategy report for you.
Right.
And then you pull out your phone to have a new pair of shoes delivered to your door by tomorrow morning. There's this profound illusion of weightlessness.
Oh, absolutely.
It all feels just entirely seamless, invisible almost. Like the future is just this ethereal cloud of software floating above us, doing our bidding without, leaving a footprint.
Yeah, but I mean, it is a brilliantly curated illusion. The tech industry has spent the better part of the last 2 decades designing these digital interfaces specifically to hide the grinding, massive physical mechanics making all those clicks possible.
Which brings us to today. Our mission for this deep dive is to completely shatter that illusion, because we're exploring the hidden, massive, and very physical weight of our digital world.
It's heavier than people think.
Oh, totally.
Yeah.
Those magical AI tools and those lightning-fast next-day deliveries you rely on every single day. They're currently pushing the world's physical power grids and logistics networks to the absolute breaking point.
And to be clear right from the start, we aren't talking about some theoretical crunch that might happen in a decade.
Right.
We are in the middle of this collision right now, actively navigating the realities of 2025 and 2026.
Exactly. And to map out what's actually happening, we are synthesizing a really massive stack of industry intelligence today.
A lot of heavy reading for this one.
So much reading. We're pulling from McKinsey's 2025 State of AI report, some urgent grid analysis from Enline Energy, market forecasts covering electric delivery fleets and roadside infrastructure from A-Power, Intel, and Global Market Insights.
Yeah, and we're grounding it all with on-the-ground data from the California Energy Commission's 2024 EPICS program.
Right. And when you lay all these sources out side by side, the through line is just undeniable. The digital revolution has finally collided head-on with concrete, copper wire, and, heavy electrical substations.
It really has.
Let's start with the catalyst driving all of this, which is artificial intelligence. But instead of just looking at the hype, let's look at what businesses are physically doing with it.
Because the reality is pretty surprising.
The data in the stack is wild. Fully 88% of organizations are using AI regularly right now. That is essentially universal adoption.
Yeah.
But, and this is the crazy part, only 39% are reporting any actual enterprise-level financial impact, meaning any real benefit to their bottom line.
And for the vast majority of those seeing a benefit,
Right.
the financial impact is, it's under 5%.
Right. It's a tiny bump.
It's a very stark reality check.
Yeah.
I mean, having access to a transformative tool and actually knowing how to extract value from that tool, those are two completely different things.
Okay, so let's unpack this, because adopting AI right now is essentially like buying a ridiculously expensive state-of-the-art gym membership, but, refusing to change your diet or your daily routine.
That's exactly.
You have the tools, the treadmills are all plugged in and running, but if you don't actually redesign how you work every day, you're not going to see any results. So if everyone has AI, why is the financial impact still so small for most?
Well, that is the crucial differentiator. And the data backs up that exact gym analogy when you look at the group McKinsey calls the high performers.
Which is a tiny group, right?
Tiny. It's a tiny, tiny slice of the market, just about 6% of the respondents. These organizations aren't using AI to, shave a few seconds off writing an email.
Right.
They are fundamentally tearing down and redesigning their core workflows. They're aiming for massive transformative innovation.
And they're committing massive capital to do it. The report says they allocate over 20% of their entire digital budget strictly to AI.
Exactly.
But wait, if they're so good at this, why are they also the ones running into the most trouble? Because the data shows these high performers experience significantly more negative consequences from their AI use than the average company.
Oh, yeah?
They're getting hit with intellectual property infringement claims and tripping over regulatory compliance left and right.
Because they're the only ones actually taking the training wheels off. I mean, if you are just using a standard language model to draft a polite memo, your risk profile is practically zero.
But your reward is also near zero.
Right, exactly.
Yeah.
The high performers are deploying what the industry calls agentic AI, and they are putting it into mission-critical environments.
Okay, let's define agentic AI for the listener, because this is a massive shift. The research shows 62% of companies are experimenting with these AI agents, and 23% are actively scaling them up.
It's the next big wave.
So what makes an agent different from the chatbot we're all used to?
Well, a standard chatbot just answers a prompt and stops. An AI agent is a system that can actually act autonomously in the real digital world.
Okay.
You give it a high-level goal, and it can plan out a complex, multi-step workflow. It can open up different software programs, execute a task, verify if the results are correct, correct its own mistakes, and then move on to the next step, completely unsupervised.
Wow.
Yeah, it doesn't need a human clicking approve at every single juncture.
So we have these highly capable autonomous agents rolling out across enterprises. But if everyone is racing to deploy these agents, why is the financial impact still stalling out for the broader market? Like, what is physically stopping them from scaling this up and replacing every manual workflow tomorrow?
Well, this is where we hit the concrete wall. Scaling AI agents to perform complex, continuous, multi-step tasks across an entire global enterprise requires an unimaginable amount of computational heavy lifting.
Right.
You cannot run an autonomous enterprise agent on your laptop's processor. It requires massive, dedicated data centers.
Which brings us right out of the cloud.
Exactly. That pulls us right out of the software layer and drops us into a massive physical constraint, the world's electrical grid.
Which means AI is no longer just a story about code. It is fundamentally a story about energy.
100%.
Because the U.S. Energy Information Administration data we're looking at, it projects U.S. electricity demand is going to shatter all previous records. They're predicting it hits 4,250 billion kilowatt hours in 2026.
And to understand why that number is so aggressively high, you have to look at the physical architecture of AI versus the traditional internet.
Okay.
Historically, if you walked into a data center, standard server rack, physical metal cabinet holding the computers, it drew about 10 to 15 kilowatts of power.
And that was the standard for cloud computing for years.
It
Right?
was. But the new AI-optimized GPU racks, the hardware required to actually train and run these complex AI agents, they demand 40 to 100 kilowatts of power per single rack.
Wait, per rack? That's insane.
A rack. And they do not take breaks. When a tech company trains a new frontier AI model, it occupies thousands of these GPUs, running at maximum power draw 24 hours a day for weeks or even months at a time.
Oh my God.
And the physical heat generated by that density of computation is just staggering, which means you then have to spend even more power just pumping in liquid cooling systems so the metal doesn't literally melt.
The scale of the money moving into this space is honestly hard to fathom. The big hyperscalers, Amazon, Microsoft, Google, Meta, they spent $200 billion on capital expenditures in 2024 alone.
Just massive investments.
Yeah, and the reports note that the next generation campuses being built right now, they demand 20 times the power of a typical legacy data center.
What's really fascinating here is the geographic concentration of that demand. You can't just sprinkle an AI data center's workload across 1,000 small buildings around the world.
Why not?
Because to train a model effectively, the GPUs have to be physically close to each other to minimize latency.
Oh, the time it takes for data to travel through the fiber optic cables.
Exactly. So you get these hyper-localized, massive power drains.
Yeah.
I mean, in 2023, data centers consume nearly 80% of Dublin's entire electricity supply.
I still have trouble wrapping my head around that.
Yeah.
80% of a major global city's power grid just go into server farms.
And in the U.S., you look at a place like Northern Virginia, which is sort of the heart of the world's internet infrastructure.
Right.
Data centers were already taking 26% of the state's power, and the projections suggest it could hit an astounding 59% by 2030.
Okay, so the obvious question here is, why don't we just build more power plants and string up more transmission lines?
It sounds simple. Yeah.
It does. But the grid bottleneck isn't just about generation, it's about connection. Here's where it gets really interesting. It's basically like trying to fill an Olympic-sized swimming pool, but all you have is a narrow little garden hose.
That is a perfect analogy.
The reports point out there are 2,300 gigawatts of power generation and storage just sitting in the interconnection queue. It takes a median of 5 years just to get bureaucratic approval and physical connection to the grid.
And the hyperscalers are trying to build these data centers in a matter of months. That extreme timeline mismatch, 5 years to build the transmission lines, 6 months to build the data center, that is the central infrastructure crisis of 2026.
So if it takes 5 years to build new transmission lines, but AI data centers are being built in months, how do local utilities keep the lights on for the rest of us today?
Ironically, they are having to use AI to save the grid from AI.
Wow.
Yeah. Because they cannot easily build new physical power lines, they have to squeeze every conceivable drop of capacity out of the existing aging lines. They're doing this by deploying technologies like dynamic line rating or DLR and grid digital twins.
Okay, let's break down how dynamic line rating actually works physically. Because I think most people assume a power line just have a static limit, like a speed limit sign.
And historically, that is exactly how it worked.
Yeah.
A power line's capacity was rated based on a worst-case scenario assumption.
Right.
Power lines are made of metal, usually aluminum and copper. When you push electrical current through them, they heat up. If they get too hot, the metal physically expands and the lines sag.
Which is bad.
Very bad. If they sag into a tree or a building, you get a catastrophic short circuit or a massive wildfire. So utilities always cap the power limit very conservatively, assuming it was a hot, still summer day.
But the weather isn't always a hot, still summer day.
Exactly. On a cool, windy day, the wind actively cools the metal. That same physical line can safely carry significantly more power without sagging at all.
So how does a grid digital twin change the game here?
A grid digital twin ingests massive amounts of real-time data. We're talking hyperlocal weather conditions, physical tension sensors on the wires, and the overall topology of the grid.
Okay.
It creates a live, virtual replica of the entire physical network. It tells the human grid operator, in sub-second real time, exactly how much power can safely flow through that specific wire at that exact second.
So it replaces a static conservative guess with absolute real-time precision.
Exactly.
They are essentially walking an invisible tightrope, and this technology is the balancing pole. And they really need it because when things go wrong, they go wrong violently. The Enline Energy Analysis highlights a terrifying near miss in July 2024 in Virginia. What actually happened there?
So there was a sudden voltage fluctuation on the network, and as a safety protocol, 60 massive data centers simultaneously disconnected from the grid to protect their equipment.
Which, I mean, sounds safe for the data centers, but what does that do to the grid?
It's an absolute nightmare scenario. It instantly created a 1,500 megawatt power surplus on the network.
Wow.
To put that in perspective for you, that is the equivalent of a major metropolitan city's entire power demand suddenly vanishing in less than a second. The electricity generated by the power plants suddenly had nowhere to go.
It's like a massive water main where someone suddenly slams the valve shut, the pressure violently backs up and blows out the pipes.
Yes, exactly. Without real-time state estimation software to instantly reroute and manage that wild swing, that surplus fries the substations. It leads to a cascading blackout that honestly could have taken down the entire eastern seaboard's internet hub.
That is the physical reality hiding behind a seamless ChatGPT prompt. But here is the real kicker. Data centers aren't the only massive new infrastructure trying to plug into this fragile grid. At the exact same time, our entire physical logistics network is trying to plug in too.
Right. If we connect this to the bigger picture, you have the stationary, localized power drain of AI data centers fighting for capacity against the mobile, distributed power drain of e-commerce.
Which brings us to the electrification of delivery fleets. The EV fleet management market is going through an absolute boom right now.
Oh, it's exploding.
The intelligence from A-Power and Intel values the market at $12.5 billion right now in 2025, and they're projecting it to hit $38.7 billion by 2034. And the economics are just impossible to ignore. Fleet operators are seeing a 40% reduction in the total cost of ownership compared to traditional diesel trucks.
Yeah, the transition is an economic inevitability. I mean, diesel's expensive to buy and it's expensive to maintain. Electric motors just have fewer moving parts. But the physical deployment of this transition is incredibly complex.
How so?
Well, imagine a typical package delivery depot on the edge of a city. For decades, they just had a couple of diesel pumps. Now they are trying to charge dozens, maybe hundreds, of heavy electric delivery vans simultaneously overnight. Most local municipal grids simply do not have the copper in the ground to deliver that kind of localized juice.
And the grid capacity isn't even the only hurdle. The research highlights brutal realities around battery degradation and commercial use. We aren't talking about a consumer driving to the grocery store.
No, not at all.
These delivery batteries are being put under massive daily strain, and they are only lasting 5 to 7 years before their capacity drops too low for a full route.
Plus, there are massive supply chain delays for the infrastructure itself. Critical telematics hardware is taking 9 to 12 months just to arrive.
Let's clarify telematics for the listener real quick. We're talking about the onboard computers and sensors that track GPS, monitor battery health, and analyze driver behavior, right? The actual brains of the fleet.
Correct. Without telematics, a fleet manager is basically flying blind. They don't know if a truck has enough charge to actually finish a route. So you have fleet managers waiting a year for the brains, replacing degraded batteries, and fighting with the local utility for grid capacity.
And yet, the consumer still expects their package delivered by 8 a.m. tomorrow.
Always.
So how do they actually adapt to keep the logistics network moving?
Well, the industry is rapidly shifting toward high-power DC fast charging. We're talking 350 kilowatts and above. And they're deploying what they call hybrid models.
What does a hybrid model depot look like in practice?
It means combining whatever limited, trickling grid power the depot can secure with massive on-site renewable energy storage.
Okay.
They install giant banks of lithium-ion batteries at the depot itself. They trickle charge those stationary batteries all day long from the grid when demand is low, and then when the vans park for the night, they just dump that stored power into the vehicles.
I have to question the logistics of this, though. A delivery van is a commercial asset. If it is sitting idle in a parking lot attached to a charging cable, it is not out making money. It sounds like an absolute logistical nightmare.
It is a massive puzzle.
How does a fleet manager balance the incredibly tight next-day delivery windows that Amazon and others demand with a maxed-out power grid that might not even be able to charge the truck when they need it?
That is the multi-billion-dollar question. And it's exactly where AI smart charging software enters the chat. You can't just plug 50 delivery vans in at 6 p.m. when the drivers finish their shifts and let them all draw maximum power.
Right.
That would blow the local substation.
So the software acts as, like, a middleman.
Exactly. The smart charging software analyzes the specific delivery routes for the following day. It monitors the real-time wholesale price of electricity, and it communicates with the grid's digital twin we talked about earlier.
Wow.
Yeah, it micromanages the charging of every single van. If van A only has a 20-mile route tomorrow, it slows down its charge. If van B has a 150-mile route, it prioritizes it. It charges them at the precise moments overnight when grid demand and wholesale prices are lowest.
It's like having an impossibly fast air traffic controller. But instead of managing airplanes on runways, they are managing billions of electrons across a fleet of hundreds of trucks.
That's exactly what it is.
And the Intel report notes this level of orchestration can save fleets 15 to 30% in pure energy costs.
It's brilliant in theory, but, this raises an incredibly important question about physical reality. When you have strained grids, brand new autonomous charging software, and incredibly tight human delivery schedules, things are going to physically break down.
Of course.
So how do we build resilience when the electric system fails?
That actually brings us to our final batch of sources, which might honestly be the most revealing. We're looking at global market insights and the California Energy Commission's 2024 EPIC report, because we have to look at the unglamorous reality of what happens when this highly complex, electrified world simply breaks down on the side of the highway.
Right. Roadside assistance is having to completely transform its entire operational model. It's no longer just dispatching a guy in a tow truck with a jerry can of gas and some jumper cables.
The global market insights data shows just how wild this evolution is. In 2026, AAA expanded into 45 different markets with 350 mobile EV charging units.
Which is huge.
It really is. If an electric delivery van or consumer EV dies on the side of the highway, they don't necessarily tow it to a station anymore. A specialized truck pulls up and acts as a massive, high-speed mobile battery.
Yeah, they can deliver 15 to 50 miles of range in just 30 to 45 minutes right on the shoulder of the road. That gives the vehicle enough juice to just drive itself to a proper depot.
That's wild.
And those roadside technicians are now having to perform complex high-voltage diagnostics on the side of busy interstates.
Right.
It requires highly specialized training, insulated equipment, and a completely different safety protocol.
It's genuinely impressive that AAA can deploy a mobile rapid charger to a broken-down EV. But let's look at the broader implications here, because this tech utopia narrative can feel very skewed. So what does this all mean for the average person? It's great to build cool mobile chargers for a broken-down EV, but are we just spending billions to upgrade infrastructure so wealthy early adopters and massive tech conglomerates can have a smoother ride, while everyone else pays the price of an increasingly strained utility grid?
That is a very fair point, and it's the exact tension the California Energy Commission's EPIC program is built to navigate.
Right, the Electric Program Investment Charge.
Yes. In their latest 2024 report, they detail how they've invested $1.4 billion of public ratepayer funds to test and deploy these new physical realities. But, and this is key, with a mandated massive focus on equity.
The numbers in the EPIC report are actually a really strong counter-argument to the tech bro narrative. Through 2024, fully 60% of EPIC's technology demonstration and deployment funding went directly to projects located in and benefiting disadvantaged and low-income communities.
Yes.
They also directed $30.4 million to infrastructure projects specifically on Native American tribal lands.
Because a transition this massive has to work for the most vulnerable parts of the grid first.
What does an EPIC project actually look like on the ground, though? Give me a tangible example of how this funding changes a community.
Okay, let's look at the Watevi Electric Truck Depot in Bakersfield, California.
Okay.
Bakersfield is a massive agricultural and logistics hub in the Central Valley, which historically means it suffers from some of the worst air quality in the country due to thousands of heavy diesel trucks idling and running routes every day.
Right.
So EPIC funded a state-of-the-art depot there that features massive on-site solar generation and battery storage. It allows these heavy-duty electric transport trucks to charge up using clean energy without breaking the local municipal grid.
Oh, wow.
Yeah. That directly reduces localized tailpipe emissions and asthma rates in a community that desperately needs the relief.
It's using the physical infrastructure to solve a physical health crisis, not just, speed up a package delivery.
Exactly.
The report also details a project called CalFlex Hub. What are they tackling?
CalFlex Hub is led by the Lawrence Berkeley National Lab, and they are addressing the home energy side of the equation. They are testing price-responsive, flexible load technologies. We're talking about smart heat pumps and smart thermostats in over 100 field sites.
Okay.
And half of those are specifically in disadvantaged or low-income communities. They are proving that you can automatically shift a home's power use away from expensive peak evening times without the residents sacrificing comfort.
That's huge.
It is. That stabilizes the neighborhood grid and drastically lowers the utility bill for the residents who need those financial savings the absolute most.
But even with $1 billion in funding and clear community benefits, the EPC report highlights the incredibly unglamorous friction of innovation. We sit here and talk about AI agents and digital twins like it's magic, but these infrastructure companies are facing agonizing year-long delays simply trying to get basic fire permits for their hardware.
It is arguably the single biggest bottleneck in the entire transition.
Yeah.
Companies are developing incredible new bidirectional chargers where the car can actually pump power back into the house during a blackout, or they are taking degraded Second Life EV batteries from those delivery fleets and repurposing them for stationary grid storage.
Right.
But they're struggling to get basic UL safety certifications.
And it's not because the tech is inherently dangerous, it's because the technology is literally too new for the regulatory state.
Exactly.
The safety standards and the fire codes haven't even been written yet, so you have millions of dollars of cutting-edge, grid-saving hardware sitting in warehouses gathering dust because a local city fire marshal, understandably, doesn't have a rubric to evaluate if a massive Second Life lithium-ion battery bank is safe to install next to a residential building.
The real work of building the future isn't just a tech billionaire inventing a faster microchip in a lab.
Yeah.
It is the deeply unglamorous, bureaucratic detail work of writing fire codes, securing permits, creating testing certifications, and ensuring equitable deployment. It's the massive undertaking of retraining an entire generation of electricians and roadside technicians to install, inspect, and repair these completely novel high-voltage systems safely.
So, to bring this all together for you listening, the next time you use an AI agent to effortlessly summarize a document, or you track a package that's magically making its way to your front door, I want you to visualize the massive, heavy, physical choreography happening just out of sight.
Millions of GPUs screaming heat and drawing power. AI digital twins frantically balancing the copper grid in sub-second real time. Giant battery banks trickling power in the dead of night, and high-voltage mobile chargers navigating the shoulders of our highways.
The digital world has a very real, very heavy physical weight.
It does. And I'll leave you with this one final thought to mull over. We briefly touched on bidirectional charging, what the industry calls vehicle-to-grid, or V2G technology. As this technology matures and gets through the red tape, and as those massive AI data centers constantly scour the grid looking for any available power to keep their models running, we're approaching a fascinating tipping point.
What's that?
Could the electric vehicle parked in your driveway, the one sitting idle 90% of the day, eventually become more financially valuable to the power grid as a decentralized smart power plant than it is to you as a mode of transportation?
Wow. Your car actively making you money while you sleep just because an AI data center 3 states away needs extra power to train a new model.
Exactly.
The future certainly isn't weightless, but it is deeply physically fascinating. Thanks for taking this deep dive with us.